Good morning, students. Today we have our third class of haloalkanes and haloarenes. So I'm taking up the questions first of all, some of the questions from the NCERT exercise. Write the products of the following reactions. First part, if to this compound we add HBr, then what will be the product? Br will add to this side of the double bond where hydrogen atoms are less, and hydrogen will add to this side of double bond where hydrogens are more in number. This rule we already know is called Markovnikov rule, where negative part of addendum adds to that side of the double bond carbon atom where hydrogen atoms are less. So when we add Br this side and hydrogen here, and double bond will change to single. This will be a product. Second part, to this compound we are adding HCl. Again addition will be according to Markovnikov rule, where negative part, that is Cl, will add to this side and hydrogen will add to this side of the double bond, and hence we will get Cl comes here, double bond changes to single, and H comes here. This will be a product. Third part, to this compound we are adding HBr, but addition is in presence of peroxide now. So if peroxide is here in this reaction, then addition will be anti to Markovnikov rule. That is, now negative part of addendum will add to this side of the double bond where hydrogens are more in number, and hydrogen will come to the other side. Hence, we will have hydrogen here, double bond changes to single, and with this carbon we have Br. This will be a product. So these are some of the questions where we are using addition reaction, where Markovnikov rule and anti-Markovnikov rule is used. Now next question, draw structures of the products. Structure of the products. First part, to this compound when thionyl chloride is added, we know alcohols react with thionyl chloride and this OH will be replaced by the Cl atom. So in place of OH, Cl will come here. This will be a main product. Along with this, there will be SO2 plus HCl formation also. So when alcohols are reacted with thionyl chloride, the OH will be replaced by the Cl and we'll get the chloro compounds. Second part, when this compound, where two OH groups are present, this OH and this OH, is reacted with HCl, and we have to heat this mixture. what will be our product? Now only this OH will be replaced by Cl and not this one. So here OH will remain as it is, while this OH is replaced by the Cl. OH and H combine to form a byproduct, water here. Why this OH is not replaced by the Cl? Because here actually we will have a partial double bond will come, which is difficult to break. So those nucleophiles which are linked with the benzene ring directly, they are difficult to replace. Now this compound is reacted with bromine, heated or UV light we can use. Then we know that substitution takes place when the halogens are reacted with the compound that has hydrocarbon part and heat or UV light is used, then hydrogen is substituted by halogen. But now which hydrogen will be substituted by halogen? This carbon or this carbon? It is in place of this carbon, one hydrogen will be substituted by halogen, and not from here the hydrogen will be substituted by Br. The reason for this thing is, if we have removal of hydrogen from this carbon, H from here, this carbocation will form, and if we are removing H from this carbon, then we will have this carbocation. This is primary carbocation, this is secondary carbocation, and we know secondary carbocations are more stable. So since here secondary carbocation will form, which is more stable, so reaction will go towards the stable side. That is why this carbon hydrogen will be substituted by halogen, and not the primary carbon hydrogen will be substituted by halogen atom. Now next questions, fourth part. If this compound is reacted with HI, there is a double bond. So HI will add to the side of the double bond according to Markovnikov rule. That means this I will be added up here to this side of double bond where there are no hydrogen atoms, and H will add to this side where there is one hydrogen atom. So addition will be according to Markovnikov rule. Double bond will change to single, and I will come here with this double bond carbon atom. When bromoethane is reacted with Ni, this reaction is Finkelstein reaction. Halogen exchange will take place. In place of Br there will be I, and byproduct is NaBr. Last part. To this cycloalkene, when bromine is added, and condition here is heat or UV light. We know when we use halogen and heat or UV light, then substitution reaction takes place. Electrophilic substitution reaction takes place and not addition. So Br2 will not add to the side of double bond. Instead, because of heat or UV light, substitution takes place. So hydrogen from here will be replaced by the halogen. So this will be a product. After these questions, next topic, physical properties of haloalkanes and haloarenes. First property is boiling point. Boiling points of haloalkanes are higher. Boiling points of haloalkanes are higher than the corresponding hydrocarbons. Now, what is the meaning of corresponding hydrocarbon? That hydrocarbon with which the molecular mass of haloalkane will match. So, if we take a haloalkane and its corresponding hydrocarbon, then boiling point of haloalkane is higher. The reason is, in haloalkanes there is carbon and halogen bond. This bond is polar in nature. Because this is more electronegative, will have partial negative charge, and this carbon will have partial positive charge. So due to greater polarity here, in case of haloalkanes there is greater polarity and higher molecular mass as compared to the parent hydrocarbon. Because of the greater polarity, there will be dipole-dipole interactions. One thing is dipole-dipole interactions are here in haloalkanes. While in case of hydrocarbons, weak van der Waals forces are there. Since dipole-dipole interaction is stronger than the van der Waals forces, so it is difficult to break this, and hence boiling point of haloalkanes will be more. And second reason is high molecular mass, because there is a halogen atom, so little high molecular mass they have. More is the molecular mass, more is the magnitude of van der Waals forces. So these forces are stronger as compared to the forces in hydrocarbons. Hence the boiling point of haloalkanes is more than the corresponding hydrocarbon. This is the first point in the boiling point. The second point in boiling point is, if we take haloalkanes with same number of carbon atoms like CH3, CH2I, CH3, CH2, Br, CH3, CH2, Cl, and then CH3, CH2F. The alkyl group is the same, but halogen atoms are different. Here we have ido, bromo, chloro, and in this compound is fluoro. The magnitude of van der Waals forces increase with increase in molecular mass. So ido molecular mass is, because of ido the molecular mass of this compound is more than this compound with Br, and this one will have more than that of the Cl, and this one will have more than that of fluoro. Hence the order of boiling points is, if we have fluoro, it will have less than that of chloro, chloro will have less than that of bromo, and bromo will have less than that of ido. Since the mass will increase like this, that is why the boiling point magnitude will increase in this order. So this one will have less and this one will have more. This one will have more than that of this one, and Br will have more than that of the I. Next point here is boiling points of isomeric haloalkanes. Isomeric means the molecular formula is same while their structural arrangement is different. Like we are taking bromobutane. This is one bromobutane. In this also there are 4 carbon atoms, but 1 carbon will come in branching. In this compound also there are 4 carbon atoms, but now 2 are coming in the site. So in this case, these have same molecular formula, but the boiling point of this one is 375 Kelvin This one is 364 Kelvin and this has 346 Kelvin. So boiling point is decreasing with the branching. As the branching increases, the boiling point decreases. The reason is with increase in branching, surface area decreases. Lesser is the surface area, lesser will be the magnitude of van der Waals forces. Hence the boiling point decrease with increase in branching. Next physical property after boiling points is melting points. For melting points, we are taking haloarenes. This is the orthoisomer and this one is a para-isomer. Out of ortho and para-isomers, para-isomer has high melting point. Para has high melting point. The reason is because para-isomer has more symmetry. Because of more symmetry, it can fit in crystal lattice better than its ortho and meta isomers. Since these are symmetrical, more symmetrical, that is why they will fit well in their crystal lattice. More close packing is there. That means it is difficult to separate the particles and hence the melting point will be more. So para-isomers, they have more melting points. This is about the physical properties of haloalkanes and haloarenes. Now I am taking one question with this thing. Arrange in increasing boiling points. Some compounds are given here. Arrange these compounds in their increasing boiling points. The first part is bromomethane. Then is bromoform, chloromethane, and next is dibromomethane. To answer this, first of all we are writing their formula. Bromomethane is CH3Br. Bromoform is CHBr3. Chloromethane is CH3Cl and dibromomethane is CH2Br2. Now looking at the formulas, see the number of carbon atoms are same. One carbon atom is here. Now there is one Cl and here we have one Br. The molecular mass of this compound is less as compared to this one. So lesser is the molecular mass, lesser will be the magnitude of van der Waals forces. Hence the boiling point of this compound will be less as compared to CH3Br. So that means if we are writing in increasing order the boiling point, then this compound will have the lowest, this compound will have more boiling point than this compound. Then the molecular mass increases here because here we have two Br atoms, and then in this one the molecular mass is a maximum because there are three Br atoms. So highest boiling point is of this compound. There are four compounds given. In increasing order when we write, this one will be at the fourth number. Then lesser than this one will be this compound with 2 Br, then will be this with the 1 Br atom, and first is this one with the Cl. This has the lowest boiling point. So answer is CH3Cl. The question is in this form, so answer also should be in this form only. So we will not write the formula, we will write it in words. This is chloromethane. So first we write chloromethane is less than that of the next compound is a CH3Br, that is a bromomethane. Less than that of the dibromomethane less than bromoform. Second question, 1-chloropropane isopropyl chloride and 1-chlorobutane. Arrange these also in increasing order of their boiling points. This has 3 carbon atoms, this has 3 carbon atoms, and here we have 4 carbon atoms. So this compound will have the maximum molecular mass out of these 3. So this one will have the highest boiling point. So at third number we will have this one. And out of these 2, this will have branching. With branching, boiling point decreases. So this one will be at number 1 and this one will be at number 2. So in increasing order, the boiling point arrangement is isopropyl chloride has less than that of 1-chloropropane, which will have less than that of the 1-chlorobutane. So these are the questions with the boiling points. After doing the physical properties, our next topic is chemical properties of chemical reactions of haloalkanes. Haloalkanes, they react with nucleophiles. And these reactions are known as nucleophilic substitution reactions. Which reactions are shown by haloalkanes? Nucleophilic substitution reactions. Abbreviation is SN. Nucleophile is a species which is rich in electrons. So if we are using this symbol to represent nucleophile, this is to show that it has electrons. And if we take haloalkane like this we know has partial negative charge and carbon has partial positive charge. So nucleophile will attack electron deficient carbon. And after attacking this, it links with the carbon and this will come out. Since it is stronger than halogen, so it will substitute this halogen and will get this compound and this Br minus will come out. These reactions are called nucleophilic substitution reactions. Now examples of nucleophilic substitution reactions, actually with these reactions from haloalkanes almost all kind of organic compounds can be prepared. Like first is formation of alcohols. From haloalkanes, alcohols can be prepared. Rx is to represent haloalkane. If haloalkanes are reacted with NaOH or with KOH or with water, and even moist silver oxide can be taken, any of these, this OH is stronger nucleophile than halogen, so it will substitute this halogen. In place of halogen, what will come here? OH will come here and this X will combine with this Na. So it is ROH plus NaX. Alcohols are formed from haloalkanes. Second is formation of ethers. Ethers are organic compound with -O- functional group in them. How we can get ethers from haloalkanes? By reacting haloalkane with sodium alkoxide. This is alkoxide. So here the H of NaOH is replaced by alkyl group. This is called sodium alkoxide. Now here OR minus is a stronger nucleophile than X. So it will substitute this X. In place of X, OR will come and these will combine to form NaX. ROR plus NaX. This is ether. So we can get alcohols, we can get ethers from haloalkanes. Third chemical property, formation of primary, secondary and tertiary amines. All three kinds of amines can be prepared from haloalkanes. Haloalkanes, when reacted with ammonia, this X comes out from here and here the nucleophile is NH2. This is a nucleophile. So this nucleophile will come in place of X. We get RNH2. After removal of NH2, one H is left here. That H will combine with X. So we are getting HX as a byproduct here. NH2 is primary amine. Now if haloalkane is taken in excess, it will attack this amine formed again. So next also the reaction will continue. Primary amine is attacked by this haloalkane and now also this X and H comes out and here in place of H there will be R. So this compound will be R2NH plus HX. Secondary amine will form. And now also reaction will continue. Secondary amine formed is again attacked by this haloalkane. Now again this one H from here and this X. HX comes out and in place of this H there will be R. So this becomes R3N plus HX. This is tertiary amine. So in this case we get a mixture of primary, secondary and tertiary amines. This reaction is called Hofmann ammonolysis reaction. Name of this reaction is Hofmann's ammonolysis reaction. After preparation of primary, secondary, tertiary amines, next we have formation of nitrites. Nitrites are commonly known as cyanides. This is the CN functional group. So when haloalkanes are reacted with NaCN, sodium cyanide or potassium cyanide, then Cn minus is a stronger nucleophile. This will substitute this X. It will come in place of this halogen and we get RCN plus NaX. This compound is alkyl cyanide. Alkyl cyanide, or we can say alkyl nitrites will form from haloalkanes. Next chemical property. After formation of nitriles, next is formation of isonitriles. Formation of isonitriles, which is commonly known as isocyanides. Isocyanides. So when alkyl halides are reacted with AgCN, in case of the nitriles we had taken NaCN, now we are taking AgCN. In this case this AgX is coming out and now this CN will come here in place of this, but it will not link as CN, it will link as NC. N is actually attacking here. So this is RNC plus AgX. NC functional group is the isonitrile functional group. So this is alkyl isonitrile or cyanides, isocyanides will form here. To get the cyanides here we take NaCN or KCN. To get isocyanides here, we have to take AgCN here. Formation of Nitro Alkenes. How we can get Nitro Alkenes? These are prepared by reacting haloalkane with silver nitrite AgNO2. Now AgX, this comes out and this NO2 attacks this alkyl and we get RNO2 plus AgX. This is the nitroalkane. Next chemical property is formation of alkyl nitrite. Difference in nitro and nitrite is nitro is NO2, nitrite is ONO. So to get alkyl nitrite, haloalkanes are reacted with potassium nitrite or sodium nitrite. So now this KX comes out and this is attacking this alkyl, but it's not a N attacking this. Oxygen in fact will attack this alkyl group and we get RONO. ONO is nitrite. So we are getting the alkyl nitrite here. So how we come to know that oxygen will attack here or nitrogen will attack here, here nitrogen will attack? This we'll do afterwards in this chapter. This we have a reasoning question. Next, after this thing, the last property here is formation of alkanes or hydrocarbons. How we can get alkane from haloalkane? If haloalkane is reacted with a strong reducing agent, lithium aluminium hydride. Reducing agent means it provides hydrogen. So this comes out and in place of this there will be hydrogen. RH will come here. RH is known as an alkane. After this we have a very small topic, ambident nucleophiles. Ambident nucleophiles. What are ambident nucleophiles? Like just now we have done nitriles, isonitriles, nitro compounds, nitrite compounds. So the groups like the CN, NC, NO2, ONO, these nucleophiles which have more than one attacking center. The nucleophile which have more than one attacking center, like here attack can be through the C. If attack is through C, the compound formed is cyanide. If attack is through nitrogen, the compound formed is isocyanide. In this case, nitrogen links, so nitro compound will get. If O will attack, then we'll get the nitrite. These kind of nucleophiles, this is one example, this is second example. These nucleophiles which have more than one attacking site are known as ambident nucleophiles. Which have more than one attacking site are known as ambident nucleophiles.